Good morning. My name is Franco Devati, and I'm the president of Failure and Damage Analysis. We have been providing continuing education courses for engineers and attorneys since 2003. Today, we are going to record one of our courses which is for the webinar, another series in the forensic engineering and accident investigation. Today's topic is the collapse of the Schoharie River Bridge in upstate New York. This accident happened back in 2000. The Schoharie Bridge is a concrete bridge, which every day over 20,000 cars cross over it without even noticing it. Any structure that is built in the water, it's a challenge to the nature. And in general, the water will try to find a flaw, try to seep through and bring it down. At the day of the accident, a volunteer firefighter in upstate New York witnessed the accident, and some of his statements that he has made we're going to use for this course. Schoharie Creek, it's a concrete bridge similar to many bridges that we see every day, and we cross over them without even noticing them. On the day of accident, which was in 1987, let me correct that, April 5th, 1987, a large white truck was on its journey to New York through a main commercial highway. The truck was heading westbound on Highway 90, and it was carrying a very heavy load of paper. On the day of accident, it started raining in the area, and it started raining very heavily. The truck driver pulled in a local restaurant to have his breakfast and then back on the road. As the volunteer fireman witnessed it, the water on the creek kept coming up and was rising fast. The flood alert emergencies were sounded, and the flood waters start getting very close, up to a point that they were going to close all the bridges. And some of the bridges were getting covered by water, and there was a point that the Route 5S across the creek just north of the freeway, the western end of the bridge was under the water. Eventually, all the bridges on the Schoharie Creek were closed, except the Thoroughway Bridge. And as the water started rising, and a truck that was carrying a heavy load of paper was going through, and all of a sudden the volunteer fireman heard a noise and a big sound, and the 18-wheeler had gone in the water, and a couple other cars followed it. Traffic came to a stop, police came to the accident site, and they saw there is a big gap in the middle of the highway, and the bridge is gone. The driver had no time to stop, and more cars followed it. Here is the remainder of one of the cars that was in the creek, and this is the trailer that was capsized and it was in the water. And this is the bridge when the half of it was fallen into the water. The police blocked the road, and also as they were surveying, the rest of the bridge start coming down. Here is some of the scene of it. And at that time, some of the officials, including Governor Como, who came to the accident site. The police diving team surveyed and investigated the site to find any survivors. And at this time, there were 10 people were missing. Governor Como expressed that there is no reason for a speculation of what has caused it, and they had to do the investigation until they come up with some results. The investigators looked for the remainder of any human bodies for the second day, and they couldn't find anyone. 10 people had died as a result of this accident. Now here a commercial highway have been cut in half. A big piece of it have fallen in the water, and they do not know if this flaw exists with any other bridges in the state or not. 10 people have died, and what they did is they decided to go over all the blueprints and see what has happened, what may have caused it, and try to find it. This bridge had been in trouble before. There was another flood a number of years ago that had shown some problems in this bridge. The Schoharie Bridge was made of reinforced concrete and steel, and sat on huge concrete piers that rested on the creek bed. These were the bases of it. In 1950s, thousands of bridges and roads were built across America because simply reinforced concrete was affordable and also strong. Here is some of the examples that we see every day. The Schoharie Bridge, when it had a problem before, that because during the flood it had some cracks in the big, huge concrete base at the bottom of it on the bed of the river. So what they had done was they had put some steel staples on top of it in order to hold it together, and this crack does not grow any further. This was the result of a previous accident and a flood that they had. And here is a typical, as the water goes and the crack had caused it at the base of the bridge. So once the water started clearing, they decided to dam the area, and in order to get to the bottom of the Pier 3 and see what has happened. They saw that some of the staples were pulled out from the base of the bridge, and so they demolished the rest of the bridge in order to have access to Pier 3. Pier 3 is this section, as you see with the red mark. And the problem that they had here, that you see the big crack. They tried to drain the water, put a dam, redirect the river, and to see what has caused it. Here is another picture of it. And now at this point, the highway is sitting at the bottom of the river. Here is another picture, and this is the crack, the blow-up picture of the crack as what has happened. The rest of the bridge was demolished. And this is when the water is drained and they start looking around the bridge and to see all the gap underneath and the crack in the base of the bridge. They found the river there was a 10-foot deep gap underneath the base of the bridge. And here's the big crack that had caused it. So the question was, what has caused this, especially with the big hole that you see underneath? An exact model was built in a hydraulic laboratory at the Colorado State University. And one of the biggest problems that when they make a bridge is the scour. A scour is similar to when we are standing at the beach on the water and the wave comes in, and once the waves start going back, it starts hollowing the sand from underneath our feet. That's a scour. And this is what happens to the bridges also. But any engineer, any civil engineer knows about the scour. And they know how to protect against it. When they did the simulation and the test in at the laboratory, they found exact same pattern that it was underneath the base of the bridge. The accident on the Schoharie Bridge had been caused by scour. But the problem is, every engineer knows that they have to put what is called ripraps. The ripraps are heavy rocks or angular rocks weighing approximately about a quarter of a ton in order to protect the sand for not removing it. And this is something basic. So when they went back to the drawing, they found some inconsistencies. In the drawings, they found in some parts they had shown that the riprap rocks had to cover all the way to the base of the foundation of the bridge. In some others, they saw that the ripraps only covers the top of it. It does not go deep enough. Also, another problem that they had found was the amount of ripraps that they had found on the scene. There was none. Very, very few. According to drawing, I believe, we will get to that, some 22,000 pound was ordered. Here in the area where they have the cracks, they found some sand and gravel, but there was no sign of ripraps. Just a few stones from the creek bed, but there was no sign of 300-pound ripraps or angular rocks that they expected to see. Here is another view of it, and the cracks. They found some around here, but nothing to the specification that was in the drawing. For some of the people, if they are not familiar with the ripraps, here is some examples of proper riprap laying around a bridge, a normal bridge, a concrete bridge that we have. Notice the amount of stone that they put in order for the water not to wash out the soil underneath the bridge. Here is a riprap repair that in this bridge, in order, since some of the soil had been washed out, they had decided to repair that, and this is how it looks after the repair. The amount of rocks and everything that they have put in order to protect the soil so the base and foundation of the bridge does not get washed away. Here is another view of it, and here is some more examples. Sorry, I was pushing the wrong one. Here is another example of it, and here is another one that they try to repair the scour problem that they had on this bridge. First, what they did is they drained the water from the river, or they make a dam outside. They cover the base, with the rock, and it's back to normal. And here is how they protected the shore of the foundation of the bridge. Here is some more pictures of it. So on the accident side, back to our case, when the flood came down, it tore away the foundation at the bottom of the bridge foundation. Here's the animation of it. Now, when that happened, this just hollowed out underneath, so the rest of the footing, the rest of the support is cantilevered from this edge, and all it takes, if a heavy load comes down here, it can break this part of the foundation of the bridge and collapse the bridge. And this is the shape, this is the test model that they did, and this is exactly what has happened. At the time of the collapse, a very large truck, heavy with the loaded with the paper, loaded with paper, is going down the highway on the bridge, and then once it goes over the heavy truck on this section, it breaks the foundation of the bridge that is cantilevered and causes the accident. According to the drawing, the contractor was supposed to deliver 2,200 cubic yards of ripraps of these these heavy rocks in the area, but they only were able to find about 60 cubic yards at the location of the accident. The scour and lack of riprap stones had caused this collapse to happen. 10 lives were lost for a few truckload of rocks. After the Schoharie Creek accident, 500 bridges across New York were all examined for the proper ripraps and safety. And this was the cause of the accidents at the Schoharie River. Thank you very much. Good morning. My name is Franco Davati, and I'm president of Failure and Damage Analysis in Houston, Texas. This is another video as a webinar for the purpose of continuing education course for professional engineers, architects, also attorneys and contractors. The purpose of this course is similar to other courses that we had as a continuing education course, either as a PDH or CE, or for the attorneys as a CLE course. Today's topic is forensic engineering. We are going to discuss the collapse of the Kemper arena. This accident happened some time ago during the 80s, and before starting that, this was a new design, and the new design sometimes can cause problems, as we may not be aware of some of the flaws that the new design might have. And at the end of the 1930s, a great project was started, which was very innovative. This is a good example of it, and that a very slender and narrow bridge was being thrown across the river for about, this was the length of it was some 2,800 feet, and it was something very unique that they had not done before. But after the bridge was built, within 4 months, they knew that it's not going to last. And many people know that the problem was the wind and the natural frequency of the bridge, and that caused it, to oscillate, and the vibration and the amplitude of that vibration going up and down, which eventually caused the failure of that bridge. Although it was a very heroic effort in design, but sometimes these heroic efforts, can have some consequences. Which brings us to today's topic. This was an unexpected accident that had happened And this was the Kemper Arena in Kansas City, Missouri. In the 1970s, there was this big push of the new design and the less expensive ways of building things. The design for the Kemper Arena actually was very admired by what it had done. As you see here in the picture, here's the arena, and the roof was going to be this space frame, 3 space frame designs outside would hold the weight, cantilevered, of the roof. You see this type of design a lot in the airports or in the arenas. This way they do not have to put a column to hold the roof. So there is no bad seat in the arena. Nobody has to look through or look the side of the column. They can see the whole event. So when they were building this, and also it could hold up to 30,000 people in the arena. The white space frame, that was a series of triangular tubes, and that was all shaped. The roof would be 60 feet above the arena floor, and it was somewhat ingenious, and it was admired by a lot of architectural magazines and newspapers. So what it would have is the cantilevered system, and the frame would hold the roof and the weight of the roof of the arena. And here where the extensions that they had would run across the roof, and with the attachments that they had from each extension, that it would get connected to the roof so it would hold the roof. Here are the designs, and each one, let me go back, would be connected to the floor, to the roof, with that kind of attachment. Now, here is the drawing of it that shows when that vertical attachment to the roof, how it is connected through the bolts that goes through and holds the weight. On the night of the accident, there was a basketball game, and there was 30,000 people in the arena. Luckily, and the day of the accident, the weather was bad, the wind was blowing hard, and it was raining very hard. And luckily, most of the people had already left the arena when the accident happened. And the whole roof, most of the roof came down. At night, I think they believe the city engineer called the builder that there is a hole in the roof of the arena, and the building manager said, well, just put a tarp over it and we'll fix it tomorrow next day. And he had mentioned to the owner of the building, there is not enough tarp to cover this hole. It's huge. So next day, when they examined the accident site, they saw all the damage and debris and everything that from the roof had fallen on the floor of the arena. Here is a few pictures of it that we're seeing. And just by accident, the architect who had designed this was in town, and he was about to get an award for this particular design that he had made for this arena from a city. So he was pretty heartbroken when he saw the building that he had designed, the roof had collapsed like that. So when they started doing the investigation, here's the hole in the roof, and they noticed
Here is the attachments that it connects, to the roof. And here's a more close-up view. And here's a more close-up view, and as you see, here's this plate, but there is no bolt in it. So the first thing that came to everybody's mind was, well, these were bad bolts. You just have to examine the bolts. The bolts caused it. The bolt caused it. And also there was another thing that has to be mentioned. Here is the vertical beam. Currently it has a side arm, but before it was allowed to rotate. It had a pin, so this was a moving and dynamic building which could adjust to wind, to the load, to the earthquake, or something like that. So they started examining all the bolts, some of them that they were sampled, they gathered over there to see what had caused them to snap. And when they examined the bolts, they saw that there was nothing wrong with them. They withstood the amount of stress or the strength that they were supposed to. And so then they took another look at the design, and here's the attachment that they had from the space structure which was on the roof in order to hold the roof at the bottom of it. Then they saw this part had failed in different shape at different locations, and they were not uniform. And when they were looking at it, for example, this one has a missing ear at the hole and everything has been ripped apart. And then they would see another one that had bended at one end, but the rest were okay. All of them, the holes, the bolts have failed. And also this would be the part on the roof that the plate that you saw would fit on top of this as it was bolted on the bottom of it. So they went back to the drawing and examined and see what happened. And what they realized was, here you have the system, the vertical shaft, which is holding the weight, can allow around this pivot point. This, in the original design, you see this arm, it was not there. So this whole thing could move. But this, they put it after the accident. So this, imagine this could move, sway back and forth, and around the pin in this area, that arm did not exist before. So you had a movable structure. At the night of the accident, it had rained hard, and that whole roof had become 4 acres of lake. It had 8 drainage, which is sufficient for a roof that size, but with the amount of rain, so you have this lake on top of the roof, and with the big wind that is coming, it's moving the water around. Just like when you look at the pond, you see a wave, you can tell that it can move the water around in this area. So what it does is in this 4-acre lake, the wind moves the water around and find the deepest end that it can stay, which would be the weakest point, because it applies the most amount of force. And once that load is applied, then this plate, when it can move with the applied load, it can become like a crowbar. So these plates had acted like a crowbar and had snapped all the attaching bolts. And this is what had caused the accident. At the part that it was the weakest and this most amount of force was applied, the plate had pulled and snapped the bolts, and once one of them go, and then the rest of them had followed in the same pattern. And that's what had caused, the accident, that just the design was not sufficient. It had not taken into consideration that's why that it should be more stiff and not be so flexible. So that's when they decided to redo it and add the side arm support to hold it from moving. And that was the cause of the accident in the Kemper arena. Thank you very much. Until the next program. Good morning. My name is Franco Davati, and I'm the president of Failure and Damage Analysis in Houston, Texas. Today we continue with another series of the webinars that we have had in forensic engineering and engineering accidents. Today we analyze the earthquake accident in San Francisco and what caused a series of double-deck highways to collapse. And we will see why it happened and some of the things that we have done ever since to stop it or to avoid this happens again. To begin with, in any parts of the world, engineers have to design for some of the unexpected situations that they may happen. Luckily here in US we are very rigid about our code requirements and the standards. For example, in San Francisco we always get earthquakes, but the damage is somewhat minimal. But in some other parts of the world, for example in Turkey, although they have copied our standards and requirement for earthquake, as they are in one of the regions and that they are very active in the earthquake zone, but unfortunately they do not follow it, and as a result the result can be devastating. Here is a few pictures that we see from some of the earthquake accident that has happened, building practically toppling down, falling on its occupants and so on, resulting in thousands of people getting killed every year. In the recent accident that we had in San Francisco, and the concern was the double-deck freeway that they had made. It was this freeway was built in 1957, and in 1957, at that time, it was built at the requirement that they had for the code at that moment, and it was hailed as one of the advancements of engineering. This is another view of it, that there is two set of highways on top of each other during the rush hours, coming and going. Then California began a program to strengthen its road. However, unfortunately, due to a budget cut in 1987, and they decided to stop it and not to do that. Here is another picture of the double-deck highway, and that we were talking about. Then in October 17, 1989, actually during a game with Oakland A's and the World Series, suddenly there was a magnitude of 7.1 earthquake in San Francisco. This not only shook the stadium, but all the surrounding the roads and the buildings were damaged. This was a big earthquake, and unfortunately the most of the damage was on this double-deck highway that was built in 1957. Here is some of the pictures. It's a two-tier highway. It's known cypress structure, and there are some areas of it that completely collapsed and sandwiched with some of the cars and people underneath. In some of them, it was so heavy that completely had crushed even the engine block of a vehicle. We're going to see some more pictures of it. This was designed that every 50 feet there was a column to support the structure on top, but they still didn't know why from this highway there was a stretch of 1.5 miles that they had seen all this damage, and they couldn't, but the rest of the highway was okay, and they couldn't understand what had caused it. So here is more pictures of it, and I believe I have a video of it too, which is, here we go. This was taken at the time of the accident, once it had just happened, as the highway had collapsed. And I have another video on the, also this one also. Here's another video as the highway had collapsed on top of the bottom one. It had pancaked. So these columns, as I mentioned, this is, before, of course this has been fixed. Every 50 feet, there was these columns that as the cars were going to support the road above them. And here is how would it happen as for the people who are driving underneath. Again, they were very curious that why this stretch of 1.5 mile had collapsed. The result was pretty devastating. When they had built this highway, some of the notables were there, and this is right when they had built the highway. This is the earliest video that they had from it, and it was hailed as one of the feats of modern engineering. And now this is how it looked after the earthquake accident. Some of these iron rods that you see as sticking out, it became, to the attention of investigators that what had caused it, why it had collapsed at the base of the highway. These columns were supposed to be very strong, and the way they were manufacturing them, these columns, they are known, they use a cage of steel tubing for the concrete in order to make it stronger. One thing they noticed that these tubings were not strong enough, and they could have been perhaps stronger, so they decided to beef up on the support. But still, they did not know that these, they couldn't put their finger that these confinements were just the only reason that they had seen such a large amount of damage and accident in this 1.5 mile. So they start looking at the soil to see if there is anything in the soil that would make a difference. And they were discovered that this stretch of the highway, it passes the part that they have seen most of the damage is where the Bay Area has a soft soil. And a lot of time, and there was always a conception or a understanding, and they thought a soft soil at the time of the earthquake will give and absorb part of the vibration and part of the earthquake, of the shake. However, they found out, so they decided to do some testing on that. And earlier when they were building it, this is a short footage of that they were putting all the pilings, in a soft ground, in the Bay Area. So the scientists put some instrumentation and did some testing, and to their surprise, when they were testing some of the aftershocks of the earthquake, they realized that the soil shakes much more violently, sometimes even twice as much when it's in the soft ground compared to the regular ground. So as a result, they start beefing up, all the highways in that area, and for example, all the connections that they had, they started strengthening underneath and on the side of the highways. Here you see they start beefing it up all the way to the top, and also if there were other ways that they could beef up the support for the connections between both highways and on top of each other, strengthening it. Here is another example of it, that how they had beefed up compared to the past. Now across the ocean, they also had an accident in Japan. In 1995 in Kobe, Japan, they had a big earthquake, which as a result caused some 5,000 people to lose their life, and since there was a lot of wooden homes in town, they caught fire. And one of the damages that a lot of them saw was at the port. But the difference was some of the damages which was in the city were somewhat a lot, but the newer construction that had a better code, they were able to withstand it, and handling it better. Here is a small footage of some of the earthquakes that how it was experienced during the earthquake. And the scenery was so bad as if the city was bombed by this one earthquake. And roughly about 5,000 people lost their life. And some of the homes were completely demolished. But one of the interesting things was that they couldn't understand by the port of Kobe, they noticed a lot of very large cracks, such as these. Usually the cracks would be a couple of inches, but they saw big cracks up to a couple of meters on the road. And they did not know what has caused it. These cracks, and this was a somewhat new port that they had built, and they had never seen earthquake damage in such magnitude which would cause these. So when they were looking at it, at the same time they noticed a muddy substance, mud was coming out of the ground at the places that they had the earthquake. This is at some part of it. Here is another part that shows the mud, very soft, refined mud was coming out of the ground, which showed what has happened is called liquefaction. Liquefaction, they simulated at the lab at Army Corps of Engineers. This is probably one of the largest labs that we have in the world that they can do this. Liquefaction is when the soil and the surrounding ground area turns to mud and start engulfing the building which they are in it. And sometimes the completely building collapses as a result because there is no longer has a foundation for it. This again was done at the lab at the Army Corps of Engineers. I believe we have a footage of it, and So here they had put some regular models on the soil to see how the effect will cause the water gets into and the soil and the sand, it loses its bearing strength. And if you have any structure or anything like that that's sitting on top of it, it's just going to sink in. This is the actual footage from the airport in Kobe where water was just gushing out from the ground. This is not a broken main line of water or anything like that. This is what is called by the liquefaction. And so we have another video on that. This is by the time that around even the airport they had this is the airport, the same footage, but different scene of it. So this is one of the things that happened during the earthquake, the liquefaction. What is the cure for that? Especially if we are in the areas like San Francisco, either they have to drain the water from underneath the soil or simply make the soil more compact. And that would be the solution for the liquefaction. With this, we conclude the presentation that we had for this earthquake accident. If you have any question, please send your email to our address and we will respond to it. We hope you enjoyed it. Thank you very much. Good afternoon. My name is Franco Devati, and I'm the president of Failure and Damage Analysis in Houston, Texas. We have been providing continuing education for professionals since 2003. Today's topic of the video is another video in the series of forensic engineering and failure analysis. For today, we are going to talk about the residential high-rise collapse in UK. This was right after World War II, where the east part of the London was bombed during the World War II, and it was demolished. So in order to revitalize, the damaged area, they decided to put some high-rise buildings. These high-rise buildings, the way they were constructed, was very economical, very affordable, and they were using concrete blocks that each one would get lifted off by a crane and would be put in a place, and all the seams around it with the concrete, they would sim it, so it would be cubes on top of cubes. And as a matter of fact, it was so efficient that on an average day, they could build 2 floors on top of each other. So some of the area that was hit, during the bombing was destroyed, was very quickly being revitalized in this method. And a lot of people could move in these beautiful new state-of-the-art buildings. And this is one example of it. As I mentioned, they could have built these in 2 floors at a day. However, on May 16, 1968, 3 weeks after one of these buildings had gone up, a building known as Ronan's Point, a lot of people that they were looking forward to moving this, they were disappointed, as in one morning, here's a few more pictures of from different angles of the building. This was a 22-story concrete building. And here, in one morning at 5:45 a.m., one of the residents goes to the kitchen in order to boil some water for hot tea. As soon as she lights up the match, unfortunately, there is an explosion, and after the explosion, she will see that part of the wall and the roof of her kitchen is gone. She herself was hurt, was taken to the hospital, And at the time of explosion, right after it, the entire corner of 22 corner floors collapsed. Now, here is the picture of it, the aerial view of it, that all the kitchens that they were in this corner of the building, they all collapsed all the way down. So there was a quick inquiry and investigation that what caused it. During the accident, 4 people died, I must admit. I must mention that. And they realized that the cause of the accident was done by a faulty gas line which had connected to the oven, and that had leaked and the explosion had happened. But what they could not understand was, well, if this was one floor, why did it cause the rest of the floors all collapse? So this is a short video of the site, and the rest of it had to be bring down in order for the repair of the building or whatever it was left. So when they looked into it, and they realized that perhaps something about the method of the the method that I mentioned was bringing down these concrete panels, putting them right on top of each other. But the problem with this method was being used, I believe, in Norway, but over there they were only making them up to 6 stories. And over here, they had, this was in Denmark, my apology. Over here they had put them all the way up to 22 floors. So here is a concrete panel construction, and here's a video of it. So as you will see, as when they bring the walls and the top, and once they have them on top of each other like a cube, they seam the edges just with the concrete. So it would be cube on top of cube. But the problem with this system was, it's like a house of cards. If one card falls, the rest of them will also fall. What they had not anticipated was, in Denmark, they do not use gas for the stove. They have other means, for their kitchen. So they had not taken into consideration possibility of explosion inside this cube. So if you imagine, if you have a cube, and once the explosion has happened, the top has gone up, the roof has gone up, and the pressure of the explosion pushes the walls to the outside. Now the floor, which is the ceiling, which is unattached, will come down to the floor, which is the ceiling of the floor below it. And that is how the whole thing had gone down. After they found out the flaw with this, this was actually pretty big, because they had built a lot of buildings in this method that had to be corrected. So what they had to do was reinforce these walls with some of the panels. They had to bolt them through the walls, so in case of an explosion, it does not fall apart again. So here is like a method that they were putting the bolts. They were putting a panel like a L-shape type, and they would be bolting the walls to the next wall, and also this would hold the roof, and also on the bottom it would be for the floor. So at least there would be extra help in case of an explosion. So as I explained it, so they went ahead and did that. But some of the buildings, they could not do that. And they had to bring the entire building down. The ones that they could be remediated and stiffened up and be secured, they did. And the ones that they could not, they just went ahead and brought the whole building down. Here is one example of some of the buildings that they could not fix it, so they decided to bring all of them down and restart again with a new set of buildings in UK. So this was another example of some of the forensic engineering and accident videos that we have been bringing to you. If you have any question, please email your question to us, and thank you very much.
Hello, and thank you for watching our webinars, our streamed webinar. Now you can go ahead and take the quiz, and after passing the quiz, you can print your certificate. I'd like to mention that our webinars are 100% money-back guarantee, that if the state board does not approve it for any reason, you'll get 100% money-back guarantee. Our streamed webinars are in compliance with the presentation requirements by the State Board of New York, Iowa, Ohio, Wisconsin, Illinois, and Nebraska. The New York engineers must take this streamed webinar between 9 a.m. until 4 p.m. During the week, Monday through Friday, but the rest of the states is on their own. There is no requirement for those times. There is no open microphone during the webinar, very much like any other company who provides this kind of service. All the correspondence and interactions are done via email. All of our webinars satisfy Wisconsin, Iowa, Nebraska, and Illinois live training requirement. Ohio Board of Engineers require a short quiz after the webinar, and all of our streamed webinars have a short quiz after them, which is perfect for the engineers in Ohio, and it also verifies the attendance of the engineers during the webinar. Thank you very much. If you had any questions, please feel free to send us an email. Thank you for purchasing our course.